This is a video on conditional probability. Now, this video is more related to the AQA and edXL A-level specifications. I do include a question towards the end from one of the Cambridge Step Support assignments. It's assignment 6, and that question kind of goes a little bit beyond the spec. But you know, I think it's good practice to do with conditional probability, so I've included it. I've included two relatively easy questions and two quite difficult questions, one of them being the Cambridge one. And then, yeah. Okay, so first of all, let's actually talk about what conditional probability is. It's basically when an event happening depends on another event, and usually you see the term given that. So, and it's written like this. So the probability of A happening given that B has already happened. For example, what is the probability I wear an umbrella given that it is raining, right? You'd expect this to be larger than the probability of just me wearing an umbrella, because if it is raining, which is in this case here, then there'll be a higher chance that I wear an umbrella, right? So those two probabilities, they affect each other. I choose at random a number between 1 and 10 inclusive. Given that the number is even, what is the probability that the number is 6? Right, so let's go through an example. Let's say I'm picking a number between 1 and 10, so these are all my possible choices. And I want the probability that it is 6, given that it's even. Now, what some people may do is to say, okay, well, the number 6, that's 1 out of a possible 10, so the answer must be 1 over 10, but that is incorrect, right? Because we want it to be a 6 and for it to be even, but we're only picking from the even numbers because we've said given that the number is even, right? So we're not actually picking from 10 numbers, right? We're picking from 5 numbers, right? So we're only picking from the even ones, so we can automatically exclude all the odd ones. So we're actually only picking from these even ones, right? And we want the number to be 6 and even. Well, if the number is 6, it is automatically even, so we just want the number to be 6, right? So we're actually only picking one number, this 6, out of a possible 5. 1, 2, 3, 4, 5. So the probability that it's 6, given that I picked an even number, is 1 over 5, right? And essentially what I did here was I said the probability of it being 6, given that it's even, is the probability that it's 6 and even, divided by the probability that it's even, i.e. we're only picking from the even numbers. This is what this means at the bottom. In this case here, we were picking from all 10 numbers, right? But here we're only picking from the even numbers because I've been told that we're only picking an even number. Because I've not picked from the entire sample, I've picked just from the even numbers, from a subset of it, right? But the probability that a number being 6 and even is the exact same as the number just being 6, because all the number 6 is even, right? This is included within this, right? So hopefully that makes sense. If number is 6 and it's even, it's the same thing as saying that the number is 6, right? Because all 6s are even. Okay, so the probability that it's 6, given that it's even, is the same thing as the probability of 6 over the probability of even, which is 1 out of 10, so the probability of it being 6 is 1 out of 10 just all together, divided by the probability of it being even, which is 1, 2, 3, 4, 5 out of a possible 10, which gives you a fifth as well. So these are two different ways to do it. This one will be more useful. It does seem a little bit more difficult with this idea of having to recognize of it being 6 and even is the same as it being 6. But this is ideally how you want to be doing it. Obviously, if a question sets itself out to be done in a way like this, then by all means do it this way. It's a bit quicker and more intuitive. But this is kind of a more general form that you'd expect to see, right? This is actually the definition of conditional probability, right? So we said the probability of it being 6, given that it's even, is the probability of it being 6 and even divided by the probability of it being even, right? Only picking from the even numbers. So in general, if I have A given B, it's the same as the probability of A and B divided by the probability of B. Now, be careful. What some people might say is, well, the probability of A and B is the probability of A times by the probability of B. And then they'd cancel the probabilities of B's, and then it would just say the probability of A. But that's not necessarily true, because you can only ever split this up into the probability of A times the probability of B, if and only if A and B are independent events, which they might not necessarily be, okay? This here is in the AQA and edXL A-level maths formula booklet, by the way, but it's written as this, right? And sometimes they might say B and A, and then they might swap around the B's and A's, but it makes no difference, right? So we'll go through an example now from an AQA past paper. I actually did this question in one of my videos, but I misread this 20% and this 80% as a half and an eighth for some reason, because apparently I can't convert from decimals, from percentages to fractions. Anyways, this is definitely just a fifth, and this is 4/5. Okay, so Craig, he takes at random a coin. Okay, and here he takes 2 coins. Okay, so he takes out one coin and a second one, and he replaces it, right? Find the probability that both coins are bronze, given that at least one of the coins is bronze, right? So the probability of both of them being bronze, given at least one of them is bronze, is the same thing as the probability of both being bronze and at least one being bronze over the probability of at least one being bronze, right? We just looked at this formula here, right? I've just applied it in this case. Hopefully that makes sense. Well, what is the probability of it being bronze? Well, the probability of it being bronze is just 1/5 all squared, right? It's just getting a bronze. Okay, hopefully that makes sense. An event, you can just times an event by itself. There's no need to think about independence because it is just its own event, right? And that equals 1/25. Okay, and let's just think about this here for a second, this probability of being bronze and at least one being bronze. If you think about this, this is the exact same as just the probability of being bronze, right? If I'm telling you I took out 2 bronze coins, right, and at least one of them is bronze, well, you'd think to yourself, obviously, or you just told me you took out 2 bronze coins, at least it's obvious that at least one of them is bronze, right? So this here we can actually just replace with the probability of bronze, right? Because this is encompassed within this. Hopefully that makes sense, right? I'll just say that one more time. If I told you that I take out 2 bronze coins, right, and I also tell you at least one of them is bronze, you'd think to yourself, that's obvious that at least one of them is bronze because you took out 2 bronze coins, right? I didn't need that second piece of information, right? Because it was already told within the first one. Okay, so this is the same thing as the probability of being bronze over at least one of them being bronze. Now, what's the probability of one of them being bronze? Well, that's just 1 minus the probability of it being silver. Or alternatively, you could do bronze, silver, add silver, bronze, add bronze. Okay, it's just quicker to do it this way. So this is going to be 1 subtract 4/5 squared because 80% is 4/5. Okay, and this gets you 9/25. Right, so now we can just plug it into the formula. So bronze over at least one of them being bronze is 1/25 over 9/25. 25's cancelled, so you get a 9. If you need more time to just think about this idea here, then take your time with it. It can be a little bit tricky. Conditional probability isn't the easiest topic to wrap your head around, so spend some time trying to understand this. Right, this next part here, I'm going to show you a formula. It's called Bayes' theorem. It's not in the formula booklet, either of them, but it might be useful to know, right? Okay, and I'll go through how to derive it now, given the conditional probability definition. And I just want to say that you don't need to know it, right? But they may, I don't know, ask a question one year that lots of people struggle with, and they expected you to be able to derive the formula. Okay, and it'll also come in handy with other probability questions. Right, so we've got this form here, right? I'm just going to rearrange it just for the probability of A and B, so I've just multiplied by this on both sides. Okay, now let's take this formula here, right, and let's swap the A's and B's, and let's just see what happens, right? So if we do that, we'll get probability of the probability of B given A is the same as the probability of B and A over the probability of A, right? So I've just taken this here and I've swapped around the A's and B's. And similarly, if I just rearrange for probability of B and A, I get this. So I just multiply by the probability of A on both sides. Okay, and then let's just think about this. The probability of A and B is the same thing as the probability of B and A, right? They're just the same things. If I told you I'm rolling a 6-sided fair die and I get a 6 and then a 2, that's the same as getting a 2 and a 6, right? So these are just the same. So if we equate these, then we'll get this. And then if we rearrange for the probability of A given B, we'll get the probability of A given B is the probability of A times the probability of B given A over the probability of B, right? And then if I just swap this around, so if I just write this on the left, right, this is called Bayes' theorem. It might come in handy. You don't need to know it, but I've just added it in as an extra, just in case you want to. So here I've just put this at the top here. Okay, let's think about Venn diagrams for a second, right? Whenever we see Venn diagrams, what we initially do is we think, okay, well, the probability of A is just this entire circle here. The probability of B is this entire circle here. The probability of A and B is this intersection here. The probability of A and not B, just make sure you know your Venn diagram facts, is going to be this slice here. Okay, and then the probability of B and not A is going to be this. Right, that's just kind of a useful thing to know. Now, usually it's wherever you can, I would always recommend turning a probability question into an algebra question, because most people are more comfortable with algebra compared to probability, and so it could translate the question into a form that's easier for you to interpret and to solve. And say you did do that, the way that you should do it, ideally, is you would say that this here is x, so the probability of A and not B is x. The intersection will be y, and then this will be z, right? And everything outside of it, so everything else, will just be 1 minus x minus y minus z, right? So it's 1 subtract this, this, and that. Okay, and this z represents just this section here, by the way. And then this x represents just this section here. And the y just represents this intersection here. Okay, so you could say the probability of A and B is the same thing as y. The probability of A and not B is the same thing as x. The probability of A or B is going to be x plus y plus z. Okay, so the probability of A given B is the probability of A and B, so that would be y, divided by the probability of B, which is going to be y plus z. Okay, hopefully that makes sense. And so this is a key fact which we'll use in the following question as kind of an example of how to change a probability question into an algebraic question. Okay, so let's say every morning I have either waffles or pancakes for breakfast. Sometimes I have both, and sometimes I have neither. You are given the following. Let's say x is the event of having waffles and y is the event of having pancakes. And let's say that the probability of x is 13 over 30. The probability of x given y is a quarter, and the probability of x given not y is 9/14. Okay, let's translate this into an algebra question, and let's say we wanted to find the probability of x and y, right? So this is what the goal is. So if we translated it to an algebra question, we'd ideally use this setup. Okay, I would use x here, y here, z here, and then 1 minus x minus y minus z is just everything else. Okay, be careful, you do need the outside, don't forget about it, because the question says I could have neither. So this outside probability here is non-zero, right? So there is a chance that I have neither, in which case I'd be on this outside section. Okay, the probability of x is 13 over 30, right? So x plus y, which is this here, is 13 over 30. So let's write that down. The probability of x given y, right? X given y, so we're in x, given that we're also in y, right? And our conditional probability formula told us that's the probability of being in x and y, so that's y, over the probability of being in y, which is this here. So that's y over y plus z. And that equals a quarter, apparently. Hopefully that makes sense. Just think about that for a little bit if you need to. Okay, similar to the first example with picking a number between 1 and 10, we're dividing by the probability of y because we're only picking from that subset, right? Given that we've already picked a y, i.e. we're automatically already just in this region here. Okay, and then the probability of x given not y. Okay, well that's the probability of x and not y over the probability of not y. Well, what's the probability of x and not y? That's just going to be this region here. Like I said, just make sure you know your Venn diagram stuff. So that's x divided by the probability of not y. Well, probability of not y is, imagine you're in y, and then it says it's we're not there, right? So we're everything other than y, right? So we can be this here, or we can be this here, right? So everything except for this circle, right? And that's going to be x divided by x plus 1 minus x minus y minus z, right? So that's this here is the probability of not y. Okay, I know that you can cancel the x's, but I'll leave that for later. And we're looking for the probability of x and y. The probability of x and y is just y. So what this is actually saying is we just want the probability of y, right? Sorry, we just want to find what y is. Okay, so let's just write down our 3 equations, right? So we've got 3 equations and 3 unknowns, right? So we can just solve this algebraically. This is just a set of simultaneous equations. Your calculator does solve these for you, so you could put it into your calculator if you wanted to, but I'll just do it manually. Let's say we took this one and rearranged for y, so we get y is 13 over 30 minus x, and let's say if I just plug in y equals 13 minus 30 over x into this one to get this. Okay, and let's say with this one I just simplified it, so I just said the x and minus x cancelled, okay, to get us that. And so, well, we know that y is 13 over 30 minus x, so we'll plug that in for here to get that. Okay, and that's fine. We'll leave that there just for a bit, and then we'll work on this. Okay, so we need to solve these two simultaneously now, because we've just got 2 equations in terms of 2 variables, x and z. So we'll solve these 2 simultaneously. So we'll rearrange one of them for an x or a z. So let's say we rearrange this one. We'll multiply out by the denominator on both sides to get this. Okay, and we'll just expand, so quarter times this minus x minus z to get us that. Okay, we'll bring the x's from this side to that side, and we'll bring this to that side, and we'll bring this to that side, and that gets us this. We'll times by 4 on both sides, just so the x is doesn't have a denominator, and we'll collect this as well. Okay, and then finally we'll just rearrange for x, divide by 3 on both sides to get this. Okay, now we've got what x equals, we can just plug this into there. Okay, and we'll do that, we'll get this. And let's start working on this denominator, but let me just use a new page because this is getting quite full. So 13 over 30 minus 13 over 30 minus a third z. This and this cancel because they're the same thing. So now then we're left with minus a third z, so that's just a third z. And then we've got minus a third z minus z, so that's minus 4 thirds z. And then we'll multiply by minus 4 thirds, 1 minus 4 thirds z on both sides to get this. We'll distribute the 9/14ths to get this. We'll bring the this 36 over 42z, this minus, to this side, and we'll bring this to that side to get that. And then we'll it looks like I've copy and pasted the same thing twice, but we'll multiply by 21 on both sides and divide by 11 on both sides to get z equals 0.4. Okay, remember one of our equations back here was y over y plus z equals a quarter. Let me just go back to that. It showed up there, but here y over y plus z equals a quarter. And so we can plug this into here to get y over y plus 0.4 equals a quarter. So if you just multiply by 4 on both sides and multiply by this on both sides, so you cross multiply, you get this. 3y equals 0.4, so y equals 2/15. And remember, we were looking for y because we wanted the intersection of x and y, so that was just lowercase y, and that's 2/15, so that is our answer. Okay, I do recommend that you have a go doing it the other way, so like without converting it into x's and y's and z's, and seeing how much more difficult that is, or how much less difficult if you prefer the other method. But yeah, maybe try doing it in a different way and seeing whether you prefer this way or your way. Okay, this next one is very difficult. So this is the step support foundation module assignment question. Okay, I'll leave this here so you can just pause and have a go at the question yourself, but I will go through it now. Okay, so we've got a disease, mathematitis, and it affects 0.1% of the population. There's a blood test that gives the correct result in 99% of people who do have the disease and 98% of people who do not have the disease. You have just tested positive. How worried should you be? I.e., what is the probability that you have the disease? Okay, so the probability of being infected is 0.001. The probability of testing positive, given that you are infected, i.e., it's given the correct result when you do have the disease, is 99%, so 0.99. Just think about that for a second. So if it gives the correct result in 99% of people who do have the disease, then the probability of testing positive, given that you actually are infected, is 0.99, because that is a correct result. And the probability of being of testing negative, given that you do not have it, is 0.98. Okay, and so what we're looking for is what is the probability of being infected, given that you have tested positive. Right, be careful. It's not the probability of being positive given that you've been tested. Sorry, it's not the probability of being tested positive given that you're infected. It's the probability that you're infected given that you have tested positive. All we know is that we've tested positive. So given that we have, what is the probability that we actually have the disease? Just be careful which way around this is, because it affects the probability quite a lot. Okay, hopefully you are able to construct these. And then I'm just going to simplify this a little bit. I'm just going to say that the probability of, well, I'll just say that infected is I, not infected is I's complement, so I dash. We'll say positive is P, and negative is N. Okay, and so let me just go ahead and just change this into a way that's a bit easier to read. Okay, so let's work with this, okay, because we've got a formula for this. It's the conditional probability definition. Okay, and that tells us that the probability of P and I over the probability of I is 0.99. Okay, now let's work with this one. Okay, so we're just doing work on them. It's the probability of N and not I over the probability of not I. Okay, and that's 0.98. We know that the probability of I is just 0.001. Okay, so we'll plug that in, and then we can just multiply by this on both sides to get the probability of P and I is 0.00099. Okay, now the probability of not I, well, you're either infected or you're not infected, right? So if you're infected with a probability of 0.1%, then you're not infected with a probability of 99%. Sorry, 99.9%. So that's 0.999. Okay, then we'll multiply by this on both sides to get the probability of being negative and not having it is 97%, 97.902% of this decimal. Okay, now let's just think about this, right? What is the probability of testing positive? Okay, now I know I've just put it here, I actually meant to animate it, but that's fine. Either I tested positive and I am infected, or I tested positive and I'm not infected. Right? Those are the only two scenarios that could ever happen. If somebody has tested positive, either they do have the disease or they don't have the disease. Right? So this here must be true. And be careful, I said the word or, so that implies that we're actually adding them. So either I'm positive and infected, or I'm positive and not infected. Right? Those are the only two things that could happen. Okay, and now let's consider the probability of not being infected, right? This doesn't mean testing negative, it just means not testing, not being infected. Either I tested positive and I'm not infected, or I tested negative and I'm not infected, right? So if I'm infected, i.e. if I'm infected as part of this, either I've tested positive or I tested negative. Right, and this encompasses everybody here, right? Because I'll just say that one more time. If I'm not infected, I either tested positive or negative. I don't know which one, but this here must be true, right? Because this sum here must just add up to everybody who's not infected. Okay, hopefully that makes sense. Now the probability of not being infected is 0.999. Okay, because that's just 1 minus this. And then the probability of n and not I is this here. Okay, so we'll plug those two in, and so we can rearrange to get the probability of being positive and not infected as 0.01998. Okay, now we've got this, we can plug this into here. This is the reason why I actually did this in the first place, why I considered this. Okay, and then this P and I we already knew is up here. So we can get the probability of testing positive to be 0.02097. Okay, and now we can work on this. Using the conditional probability definition, we've got I and P divided by the probability of P. Okay, well, I and P, well, we already know that's the same as P and I, so that's just 0.00099, divided by the probability of P, which is 0.02097, and that gets us roughly 4.7%. Okay, and that is our answer. Now, here, the reason why I knew to consider this and this is because I preemptively knew that this here would give the probability of I and P over the probability of P. And I knew that, okay, well, I knew the top one, but I didn't know the bottom one. So I somehow had to figure it out. So I thought to myself next, well, who is everybody that could be tested positive? Either I tested positive and I'm infected, or I tested positive and I'm not infected. Okay, then I realized, oh, wait a minute, I don't have this. Okay, and that is what led me to consider this. Okay, you can consider the probability of being infected, so that would be the probability of being infected is the probability of testing positive and infected, or testing negative and not infected. Okay, but I thought but that doesn't really help me, because wait, sorry, I might have said that wrong. What did I say? The probability of being infected is positive and infected, or negative and infected. Okay, that's what I meant to say. But all of those were just in terms of i's, but I wanted I dash. So I thought, okay, well, let me instead consider the probability of not being infected. So which led me to this equation here. And then I found this, which helped me to use in that. And then that got me this, which I used in that. And that got me my answer. Right, so it's kind of just like, it's kind of thinking about what you need and thinking about what you have and trying to relate all of those together. Okay, you could have used Bayes' theorem, the one that I showed earlier, but I decided not to, just because it's not really required. But yeah, I think this way is a bit more intuitive, and I think it shows a stronger understanding of the question. Okay, now the reason why this question was even written is so that you would be thoughtful of the probability of being infected, given that you are positive, as being a completely different probability of the probability of being positive, given that you are infected, right? So it's different if I say I given P compared to P given I. Those are two wildly different probabilities, right? So just because I tested positive, just because I'm infected, the probability, given that I tested positive, the probability of me being infected is still very low, right? Just think about that in a real world scenario. I could test positive for something, but the probability of me actually being infected could still be incredibly low, as only 4.7%. Okay, which is why it's important to do multiple tests to get rid of false positives and false negatives. Okay, so it's kind of the reason why this question was written, and I hope this helped you to understand conditional probability a bit more. This isn't a complete guide on all of conditional probability. There is a lot more to learn, but if you're able to do something like this, I mean, you should be completely fine with all of the probability that they give you at A-level maths, because they wouldn't ask a question this difficult, I don't think. The other one that I showed you with the Venn diagram, that did come from an AQA paper. I just changed it a little bit. So that is definitely something that they could ask you, but it's not as likely. That is quite a difficult question. It's not been standardized, that other question with the Venn diagram. So but they could still ask a question similar to that in a paper. So just make sure you have a very good grasp on conditional probability. I hope you enjoyed the video. Thank you for watching.